All right, well, welcome to another lovely day. Lovely because we get to do trig. It's also kind of sunny outside. But today's plan is to continue working on identities. Up to this point, we've developed quite a few. We're going to develop a bunch more today that all kind of come back to the sum and difference of angles identities. But before I do that, I want to turn it over to you guys, see if there are any questions you guys have about any of the homework or anything that we've talked about so far. Any of those you'd like to see?
Yeah, I was kind of confused with one of the questions.
Let me know which one, Nicholas, and we can take a look at it.
On number 11, 10 was kind of similar, but I was able to find that one. But number 11, like I can't get A until they give me the answer, and then I can figure it out. But
Okay, can you tell me which section? Which
oh, sorry, 8. It's a chapter 8 review.
Okay, so chapter 8 review number 11. All right, I'll put that on the list. Any others? Go ahead, Danielle.
9.2, 5 and 6, either or, if we could do one of those.
Okay, we can definitely do that. Put that one on the list. Any other ones? All right, well, I'll tell you what, if anything else pops up, go ahead and throw it in the chat box and we can go and take a look at it. But let me go ahead and share my screen here and we'll go see if we can figure out these assignments or these problems. All right. Okay, so we'll start with the chapter 8 review question number 11. All right, so it says solve sine of x equals negative 0.6 on the interval 0 to 2 pi. So we're trying to find any angle between 0 and 2 pi whose sine is negative 0.6. Okay, so let's first just think about where these answers are going to be. What quadrants are x going to lie if sine is equal to negative 0.6?
Would it be 3 and 4?
Okay, perfect. Yep, they're going to be in quadrants 3 and 4. So obviously when it says here there are two solutions, A and B, well, one of them is going to be the quadrant 3 angle and the other one's going to be the quadrant 4 angle. And then they specifically said that A is less than B. So that means that A is our quadrant 3 angle and B is our quadrant 4 angle. Okay, so I always like starting there just so I know what I'm looking for. And I'll also know whether my answers are reasonable or not. Okay, so now that we know where to look, how are we going to get a number for this? What are we going to actually do?
So I was trying to use like the inverse of sine, but yeah, that's kind of like as far as I was getting. And I could get B by like adding or subtracting that by 2 pi. But yeah, and then I just can't get A.
Okay, but I love it, Nicholas. You're right. Let's use inverse sine. This is one where we want to use a calculator because this is not anything that's a nice angle. Which do we want, degrees or radians?
Radians, right?
Okay, why radians? I agree. Not only because I love radians, but there's something here that specifically tells me I should be doing radians.
Honestly, I'm not 100%. I just have seen that like the farther we're getting in, the more we're just going to be using radians. So
Okay, well that's actually very true. But there is something on the way that this question is asked that specifically tells me I want radians.
I guess because you're trying to find like the theta of sin.
So it's this right here, the fact that it says I want to be between 0 and 2. Since there aren't any little degree symbols on there, right? That tells me that these are radian amounts. So I'm looking for radian values. But you're right, Nicholas, pretty much going forward, we're gonna stick with radians anytime we're just doing mathy stuff. If we're doing applied stuff, we tend to go to degrees because, like, you know, engineers and scientists haven't figured it out yet. They'll come around, don't worry. All right, so let's do inverse sine of negative 0.6 in radians. And the number that I got was negative 0.6435, and then a whole bunch of other stuff, 0.11087993. All right, so I get a lot of decimals, but you should get a number around negative 0.6435. Okay, but that is not between 0 and 2 pi, right? That's a negative number. But what I do know is that that is in quadrant number 4. I know that the angle that we just got, the negative 0.6435, that's in quadrant number 4. And the reason I know that is because of the restriction on inverse sine. Let me go back to a whiteboard here and show you what I mean. So what we saw before for inverse tangent, that's going to give us x's that are between minus pi over 2 and pi over 2. And I wrote less than or equal, and it should have just been less than. Hold on a second. That was the restriction that we had to put on tangent so that inverse even made sense. And what I know about these angles is that these are in quadrant 4 or 1. Well, quadrant 1 means it's positive, and quadrant 4 is going to be negative. So since I'm putting in theta equals theta, since I'm putting in a negative number, I know that this has to be in quadrant 4. So what we just found is an angle that's down here, where this is negative 0.6435. All right, so cool. Unfortunately, like I said, it's not between 0 and 2 pi. So here's what we're going to do. And in fact, I think, Nicholas, you said something about how you added 2 pi, right? If we add 2 pi to this, that's going to bring us right back around, one full circle. And now that's going to be a positive angle. So the quadrant 4 one, we're going to get that by doing the negative 0.6435 plus 2 pi. So it's still coterminal, means it's in the same quadrant, but now that number is going to be between 0 and 2 pi. And let's see, my calculator says 5.63968, something like that. Obviously, it goes on forever, but all right, so that's one of my answers. That's the one in quadrant 4. So now let's go find that sucker that's in quadrant 3. Because we know there also needs to be one here. So we're looking for this angle. Now, I like to draw the picture because it definitely helps me visualize what's going on. And I don't know if it just helped you, but I definitely know what this angle is right now. How big is that angle?
You just add pi to that, to the.
Yeah. So that's the positive. This is 0.6435. So if I want the whole thing, so this is going to be my quadrant 3 angle, it's going to be pi plus the positive 0.6435. So really what I'm doing is I'm making use of the reference angle idea. Remember when you have a reference angle up here, in the second quadrant, it's pi minus that reference angle. In the third quadrant, it's pi plus that reference angle. And I know this reference angle is just the positive of what I got for my inverse tangent.
Yeah,
All right,
definitely
so
helps to draw it out.
yeah, and I think as soon as you do that, then you can start seeing the different pieces and where they belong. So I highly recommend making use of that. Anyway, so now we can use our calculator. You know what? Let's see, 0.6435. It's around 3.785, plus or minus a little bit. I don't remember what this question said in terms of how much to round it or whatever.
I think it's by the third number.
The third decimal spot. Okay, so then that should be enough because the next one after this is actually a 0. So, but anyway, regardless of where they tell us to round it, at least hopefully now you're kind of seeing my approach.
Yeah, definitely, thank you.
So I really do two things that I want to definitely highlight here. The first is I think about what quadrants my answers are going to have to be in. And that's going to tell me by the sign, the plus or minus sign, and which trig function we're using. Right? So like in this case, since it was sine. Did I write tangent? It was sine the whole time. Yeah, it was sine the whole time. Turns
Luckily,
out
it's
that,
similar, just one has brackets, one has parentheses.
yeah, well, yeah, exactly. Luckily that didn't change our boundary there. But again, so I start with where is sine negative? So I know where to look. And then I make sure I realize where the inverse trig function is bringing me, right? Which of the quadrants is bringing me to, because then I can adjust accordingly, right? Sometimes it will bring you the angle you actually want. This case it didn't, but had it been, let's say, inverse cosine, so cosine inverse of negative, then that would have brought us to the second quadrant and that would have been one of the angles we wanted, right? But in this case it didn't. But anyway, so I look at where my answer is going to be and where's my inverse trig bring me, and then I can use that to kind of piece it together. So
Yeah, I think that's why I was able to get 10 because they were using cosine on that one.
okay, yeah, and then yeah, cosine is beautiful. This is another reason why I like cosine, why cosine is my favorite trig function, is with the inverse cosine, yeah, it just, whatever it gives you, it gives you. You don't have to fiddle around or anything. You're going to be good to go. All right, so let me just consult the chat. I saw somebody put something in the chat here. Section 8, number 12. So Anna, can you tell me which of the section 8 you mean? Same one, chapter 8 review?
Yep, same one, just the next question.
Okay,
Thank
cool.
you.
Yeah, no worries. So let's go grab that while we're here before we go change to a different section. Okay, so this one we have solve 8 sine of pi over 4x equals 4. And we're going to find the 4 smallest positive solutions. All right, so let me go ahead and write this down. And we'll hop back to the whiteboard. All right, so for this one, we've got 8 sine of pi over 4 times x equals 4. All right, so I want to get the value for x. Basically, I want to know, what do I plug in here so that I get a true statement? In order for this to be true, I need the sine of pi over 4x to equal 1/2. Because then I've got 8 times a half is 4. In essence, basically what I did was I just divided that 8. I moved that over here. Now, I'm going to rewrite this for a second as sine of theta equals 1/2. So let's just think about this for a minute. Can you tell me angles where sine is equal to 1/2? It should be on our chart.
Pi over 6.
Okay, so that's one of them.
And then 5 pi over 6.
Okay, another one down the list is 5 pi over 6. And remember what they said, they wanted the 4 smallest. So there's 2 of them, which means we need 2 more. But if you look at your chart, you don't see any more, right? Okay, so where's the next one going to show up then? It's clearly not between 0 and 2 pi. How about this? Think about the period of sine. What's the period of sine? How often does it repeat?
What, pi?
Not pi.
And
That's
2 pi?
Yeah, there you go.
Pi
So it's
over-
one, it's one or the other, right? The periods of all these things we've seen are either pi or 2 pi. So the next one's going to actually show up at pi over 6 plus 2 pi. And then the one after that is going to be 5 over 6 plus 2 pi. If I wanted another one, it would be pi over 6 plus 4 pi. And then the one after that is going to be 5 pi over 6 plus 4 pi. And then so on and so forth. So we use the values on our chart. And that got us 2 of them. But because it asked for more, we had to do more cycles. And we're just going to keep doing cycles until we get enough of them. So these other 2, if you get common denominators, this is 13 pi over 6. And this is 17 pi over 6. All right, now we're not done, right? Because we're trying to find values of x. And the reason that I did it this way, calling it a theta, is just I think it's a little bit easier for us to go through the chart and find our things. But now let's realize what that theta actually is. That theta is actually equal to pi over 4x. So we're going to get pi over 4x equals pi over 6. And we're going to need to solve that. All right, well, I'll just multiply both sides by 4 over pi. The pi's are going to cancel. 4 over 6 reduces to 2/3. So there is one number, and this is the smallest positive number, that if I plug in here is going to give me a true statement. Because 2/3 times pi over 4 will be pi over 6. Sine of pi over 6 equals 1/2. 1/2 times 8 equals 4. All right, well, to get the other ones, we're going to do exactly the same thing. We just change these numbers. Right? So now, again, we're going to multiply by 4 over pi. That's going to give us 26, which reduces down to 10/3. All right, the next one, 13 pi over 6. And I believe that that gives us 26/3. And then the last one, 17, I think should give us 34/3. But there are many more that are going to make this true. Right? I mean, all we need is that theta to be coterminal to pi over 6 or 5 pi over 6, and we can do that in an infinite number of ways. So there are an infinite number of x's, but these are the smallest, the 4 smallest positive ones. So this little trick, I don't know how much you've seen this in algebra. We do this in calculus all the time, where we do a substitution, where we take something that looks kind of ugly and we replace it with another letter. We just go, hey, let's just take that whole thing and make it a U, or make it a theta, or make it a insert your favorite letter. Because a lot of times it helps us see what we need to do, and then we can always backtrack and resubstitute to find our answer. All right, so questions on that one? Does that make sense?
Is the 17 over pi because you did pi over 6 plus 3 pi, or where's that?
No, so that was 5 pi over 6 plus 2 pi.
Plus 2 pi, okay.
So that was the second quadrant angle that we ran into the second time. All right, any other questions on that one? And let me just circle back to you, Anna. Does that help kind of see where to go with this?
It definitely does. Thank you.
Okay. And you can apply this to any equation, right? I mean, it doesn't have to be this specific one. But what I always do is I try to figure out, you know, what the sine, cosine, tangent has to equal, because then I can find my angles. And I always do a substitution like this to help me see it. All right, cool. So let's then hop back over to the homework sets and go find the one from 9.2. All right, back out of this. I really should have put something in so I can get some points. My grade is horrible right now. I have so few points in my homework. Hopefully this professor's not too much of a dick and will still pass me. All right, so numbers 5 or 6, doesn't matter which one, Danielle, you good? So we'll go ahead and just take number 5. All right, so this one says solve sine of 4x cosine of 8x minus cosine of 4x sine of 8x equals negative 0.9. So this sorta a little bit kinda looks like what we did before, but definitely sort of very much doesn't, right? Like it's not just one trig function, it's a whole bunch. But here's where the identities are going to help us out. The key to this is recognizing that that left-hand side, the sine of x cosine of 8x minus cosine 4x sine of 8x, that actually is in one of the identities, in one of the sum and difference identities. So let's see if we can figure out which one it is. This actually just reminds me. I put in something up on the canvas. Let me show you real quick. If you go over to files, I don't know if anybody's ever gone and explored over there. And it has a bunch of things that you can actually access. You can't access all of what I have here because some of those are quizzes and exams. But if you go to yours, you're going to see this one is called full identity sheet. It's also where the trig value charts are and all that. So in case you ever want to go back for those. But I went ahead and I put one of these in here as well. And this has all of the identities, including ones that we have not done yet. Okay, so when you look at this, if it ever decides to pull up, spinning wheel of death, let's try this again. All right, or not. Well, okay, if you end up pulling this up, it'll have all the identities on there. So it'll have like the reciprocal, the quotient, the Pythagorean, all that. But now it also has the sum and difference of angles identities, the double angles, and so on. I'm not going to sit here and wait for that to come up. So instead, let me jump to the whiteboard, clear all this stuff, and just remind you of the sum and difference of angles identities. So we had sine of alpha plus beta. That was equal to the sine of alpha cosine of beta plus the cosine of alpha sine of beta. We also had similarly one for the difference in angles inside of sine. And what changed over here is this is a minus sign. Okay, so there's your sine of alpha minus beta. For cosine, we had cosine alpha cosine beta minus sine alpha sine beta. And then the other one, when it was subtracted, looked the same except for there was a plus. Okay, and then we also had the one for tangent. I'm going to go ahead and combine those, show you that little trick I pulled before. Right, tangent of alpha plus or minus beta, and that's equal to tangent of alpha plus or minus tangent of beta over 1 minus plus tangent of alpha tangent of beta. Writing it as minus plus just makes it so that the top ones correspond with each other. All right, well, anyway, so we developed these last time. We also did double angles that came from these, but we developed these last time. Now, if we look at number 4, the left-hand side of that equation look like sine of 4x cosine of 8x minus cosine of 4x sine of 8x. And that equaled, was it negative 0.9? Okay, so you look at this, it's horrible, it's ugly, it's nasty. But hopefully you notice that not too far to the side here is an identity that has this form. We have sine of something times cosine of something else, sine cosine, minus the cosine and sine of those things swapped. All right, so here's what we can do. We can actually use that identity to change this into sine of 4x minus 8x equals negative 0.9. All right, so again, this was just using that identity. We just had alpha was the 4x and beta was the 8x. Okay, so this is sine of negative 12x. I'm going to use the odd property to pull the minus sign out of the sine. And then since both sides are negative, I can actually...
So that's not sine of negative 4x, right? It's...
Oh, no, you are right. That was wishful thinking on my part, maybe. I don't know. Look, I'm not very good with subtraction. Just so you know, I'm not much of a math guy, so I just wing it all the time. Thank you for that, though. All right. So, yes, 4 minus 8 is negative 4. And then the odd property of sine, the odd identity, lets me pull that minus sign out front. And so now we're here. And this should look a lot like the one that we just did. Right? The one that Anna asked about from chapter 8, where we've got sine equaling some kind of a number. All right, so let's think about how we're going to get the answer to this. Let's do a little substitution again, kind of like I showed you before. I'm going to call this sine of theta equals 0.9. And to get the answer to this, we need to do inverse sine. And that's something our calculator is going to be more than happy to do for us. Oh man, this is actually kind of cool because this is sort of like the question that Nicholas asked about. We get to tie both of those things together. So let's think first of all, what quadrants are sine positive? Like where is sine itself positive? Which quadrants?
Quadrant 2
Quadrant 2
and 1.
and 1. Okay, so we know from this that this has to be quadrant 1, quadrant 2. What is the inverse sine going to give us? Which quadrant is that going to bring us?
Quadrant 2,
Let's try that again.
1.
There you go. Okay, that's going to be quadrant 1. You had a 50-50 shot. So the reason we know it's quadrant 1 is all of the inverse trig functions bring us to the first quadrant if it's positive. That's by design. Okay, so since this one was positive, it's going to be quadrant 1. So this is actually going to find us the quadrant 1 angle. If we want the quadrant 2 angle, well, then we'd use the reference angle stuff, kind of like we did in the question that Nicholas asked, and go from there. Okay, but luckily, we don't have to do that because they ask us to find the smallest angle, if I recall correctly. Let me just double check that real quick. Well, I've subsequently lost the assignment, but I think it said find the smallest one. So the smallest one is going to be the quadrant 1. All right, so we'll do our inverse sine of 0.9, and I am going to leave it in radians. I don't think they specifically told us, but we're going to get in the habit of doing that. So this is 1.119769515, blah, 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 blah. All right, but again, that's not my answer. That's not the number I'm going to put into the box. Why not?
Do I have to find X?
Yeah, we need to find X. Remember we did the substitution. Well, this number, that's actually 4X. So to get X, I actually have to take this and divide it by 4. And so I'm going to get 0.2799423. That's probably more than enough decimal places for our answer. All right, so this actually combined a lot of the stuff that the first 2 questions you guys asked about. But the key to this one is recognizing that all that horrible nastiness with sines times cosines and all that can actually be simplified using that difference of angle identity for sine. So when you see a bunch of sines times cosines, start thinking sum and difference of angles identities, but in reverse. All right, so is that good, Danielle? Does that kind of help you see what you need to do for these? And,
Yes, thank you.
and you should
And
be
then
good for
just-
number
yeah.
5.
Number 5 is good. I just did it with you with my numbers and I got it right. So thanks
Okay.
for that. And then just for number 6, you would to start it, you would convert it to radians because that one does give you degrees, or do you just do the whole thing in degrees?
No, you could go ahead and do it in degrees.
Okay.
Let me actually go jump to that one. I'll go take a look at it. So same section, but number 6, right? Yeah, so this one, I would go ahead and leave it in degrees. You know what? Let's go ahead and just work it out. So we got sine squared of 14 degrees plus cosine squared of 14 degrees minus sine of 45 over cosine of 45. Okay, now the 45-degree ones, we actually know those values. Those are on our chart. So we could go ahead and go to our chart and get those values, but I'm not going to yet. Instead, let's use our identities to simplify this. Okay, so let me just clear this real quick. So we had sine squared of 14, not 114, 14 degrees plus cosine squared of 14 degrees minus sine of 45 over cosine of 45. So what I would recommend we do is start with identities and start simplifying this down. Like, look at the sine over cosine, right? This bit right here. What does sine over cosine equal? What trig function gives us sine over cosine?
Tangent.
That's just tangent. So this is the same as tangent of 45.
And if the equation gives you two different numbers, like mine is sine of 55 over cosine of 35, would you, it would just be tangent 55 over 35?
No. Well, I'll show you what we have to do there. That one, yeah, that one's not as nice. I'll get there in a second. Okay, so now check this out. You see a sine squared, you see a cosine squared. That should get you all excited. But remember, be careful, because we've now seen another identity that involves sine squared and cosine squared, specifically the double angle of cosine. But these, since they're being added, sine squared of 14 degrees plus cosine squared of 14 degrees equals 1. Doesn't matter what that angle is, as long as they're the same angle, right? As long as they're the same angle, that's going to work out. All right, so already this is looking way nicer. It's just 1 minus the tangent of 45. All right, well, tangent of 45 degrees, if we look at our chart, that's just equal to 1. So it turns out that this horrible expression is actually just equal to 0. So identities can really help you in situations like this one. So Danielle, can you read to me what yours look like? Because you said it was like 55 over 35 or something like that.
Sure. Yeah, it's sine squared 76 degrees plus cosine squared 76 degrees minus sine 55 over cosine 35.
Huh. It surprises me that they did that to you, but not really. Okay, so here's the deal. We can start the same way, right? Sine squared plus cosine squared, since those angles are the same, boom, that equals 1. Now this next one, I've got sine over cosine. Just because I have sine over cosine doesn't mean it's going to be a tangent. And since these angles are not the same, I can't just make that a tangent. So somehow we're going to have to figure out some other way to simplify those. All right, well, take a look at 55 and 35. What's special about those two angles? I mean, other than the fact they're 20 degrees apart, but that's just.
They're both in quadrant 1.
Okay, they're both in quadrant 1.
And they're like each other's reference angles. Is that what
Okay.
the term is?
So the word you want isn't reference, but complementary. Okay, so here, just think about this. If, let's say, this was 55 degrees, what's the other angle in the right triangle?
35 degrees.
35 degrees. So these are what we call complementary angles. All right. Does that help you see how we can deal with these? They're complementary angles. They're complementary, start CO. So these are cofunction. We can use the cofunction identities. What we saw is that now we had it with pi over 2s, but we can turn them into degrees. So the cofunctions swap for complementary angles. There are also the other identities for tangent and cotangent, same thing. Secant and cosecant, same thing. All right, so what this tells me from my complementary angles and cofunction identities is that, for example, this top one, sine of 55 degrees, that's actually the same as the cosine of 90 minus 55, which is the cosine of 35 degrees. So those guys are actually the same. Sine of 55 and cosine of 35 are identical. So I'm going to go ahead and change it to the cosine of 35. Okay, well, now that I can reduce. Cosine divided by something divided by itself is just 1. And oh, hey, look, that one gave us 0 as well. So that time we had to use the cofunction identity to help us simplify. All right.
Thank you.
Yeah, you're welcome. So let me just give you guys some general, because I can just imagine, I don't get to see anybody's faces because nobody shares them, except Danielle and Nicholas, thanks. But so I can't read your faces, but I can imagine, because I've seen faces in these classes for decades. At about this point, people start getting that look on their face. That's that look of, it's a little bit defeated. It's the, how the hell am I going to do this when it's my own quiz and and Bruce isn't there to help me out, and how am I going to recognize which of these millions of identities I want to use, and blah, right? Like it's a little bit overwhelming too, right? So it's defeated / overwhelming / you don't give a shit, right? Let's not lie. There's some of that in there too, right? So in terms of helping you with these simplifications, things to watch out for. All right, so these are just things to look for that I highly suggest. So 1, watch for the squareds. Sine squareds, cosine squareds, they are your best friend when they show up in pairs. Always look for those to reduce them. Make sure your angles are the same. You have to have the same angles for any of our identities, right? So whether we're talking about quotient, reciprocal, it doesn't matter. They have to be the same angle. So in a situation like this where you don't have the same angle, start thinking, hey, is there a way I can make them the same? And often that's from a cofunction identity. That's really where we use those. Other than that, my other big piece of advice for all these identities is practice going right to left. Practice going right to left. You are very used to always just going left to right. We read left to right, we do math left to right, left to right, left to right. The identities are extremely useful, also right to left. And the one that we did, the first one Danielle asked about, the one that had the like cosine of 4x and sine of 8x business, that was one of them where if we recognize going the other direction. So practice going the other way with these things too. Don't just learn them as sine of 2 theta is 2 sine theta cosine theta. Like, yeah, that's great. But being able to go the other way from 2 sine theta cosine theta back over to the sine is useful as well. The other thing I'm going to just remind you about these is that it takes practice, takes time getting familiar with them, and it's unrealistic to think, oh, you saw me develop them, I showed you an example or two, you got them down. No, that's nonsense, right? It's just like anything else, you got to practice it yourself. So anyway. All right, so with that, I think we're probably good looking at some of that homework and reviewing. So today we're going to develop some more identities. We're going to build on what we have, and I'm going to show you some more. So far, the kind of the new ones were the sum and difference of angles of identities, and then we use those to make double angles. Well, today I'm going to show you half angles. There's an identity for cutting angles in half. I'm going to show you what's called power reduction. Guess what it does? It reduces powers. Mathematicians, I swear to God, we name everything exactly what they are. All right, so I'm going to show you power reduction. And then if we've got time, we'll just sort of see how we're doing. I'm going to show you the sum to product identities and the product to sum identities, which take you from adding to multiplying or from multiplying to adding. Oh, shocker. All right, so we're going to have a whole bunch more, but they all come from ones we've already built. Everything we're going to do from here on out always goes back to ones that we've already constructed. All right, so I'm going to hop up to the whiteboard. I'll be right back with you. All right, so again, just to remind you what we've seen so far in terms of identities. I'm just going to make a list. I'm not going to write them all out. Okay, we've seen the reciprocal. We've seen the quotient. We've seen the Pythagorean, the even odd, the cofunction, the sum and difference of angles, and most recently, we saw the double angles. So it's getting to be a rather long list. And like I said, we still have a whole bunch more that we're going to develop to add onto this. Okay, but like I said, they are all going to make use of ones that we have recently seen. So the most recent ones were the double angle, and I do want to bring those back just because, well, you guys didn't ask any homework questions about them yet because those aren't due yet, but I just kind of want to remind you these. So the double angle identities were exactly what they sound like. We start with two angles, so sine of 2 theta, and we saw that it became 2 sine theta cosine theta. The cosine turned into cosine squared minus sine squared. But there were two other alternate versions of this that we could use if we use the Pythagorean to substitute in. One of them was 2 cosine squared theta minus 1. And the other was 1 minus 2 sine squared theta. So those just came from substituting in the Pythagorean. The reason we like these is they only have one trig function instead of both. And there are many times where it's handy, where we'll know one but not both. And that way we don't have to find the other one. So that was the cosine of 2 theta. And then lastly, we had the tangent of 2 theta. And that one was equal to 2 tangent of theta over 1 minus tangent squared. All right, so we developed these, but we really didn't do much with them. So just to kind of refresh ourselves and to play with this, let's actually prove an identity. Okay, we're going to prove an identity using these. And we're going to show that the cosecant of 2 theta minus the cotangent of 2 theta is equal to the tangent of theta. All right, so let's just practice identities here. Remember what we do. We start on one side. We work only one side. And we use identities in algebra and simplify it until and keep going until it looks like the other side. I always suggest working with the uglier side, which in this case, I think for sure is the left. This left-hand side looks pretty nasty. Okay, and then you look at these and you go, well, this sucks. We don't actually have any identities for cosecant of 2 theta or cotangent of 2 theta. All right, so what do you think would be a good first step with this left-hand side then, since we don't actually have identities for cotangent and cosecant? What's my advice for what to do if you have no other clue what to even begin doing?
Convert to sine or cosine.
Yeah, thanks, Jared. How about we turn these into sines and cosines? So cosecant, we know cosecant is 1 over sine. If nothing else, that gives us an identity that we can fire in here for sine of 2 theta. And then cotangent, in terms of sine and cosine, is cosine of 2 theta over sine of 2 theta. And again, I can put stuff in for these because I've got identities for them. So when all else fails, go to sines and cosines. This now suggests an algebra step that I want to do. I want to just combine these into one fraction since they have the same denominator. And there was a reason that I wanted to do that other than because I don't want lots of fractions. But think about what I'm going to want to do at this next step. I'm going to want to substitute in using the double angle identities. If I combine it into one fraction, I only have to substitute in for that sign 1 time instead of twice. It's the laziness in this mathematician. By the way, mathematicians are lazy. You know this, right? To be a good mathematician, you got to be lazy. You got to see the shortcuts that you can take and then take the shortcuts. All right, so now let's use the double angle identities, right? Because I've got sine of 2 theta. So I can use this one up here. Let me just go ahead and put that in. So on the bottom, we're going to get 2 sine theta cosine theta. All right, and then on top, I've got a cosine of 2 theta. So we want to do the same thing. Uh-oh, but I have 3 choices. I can use any one of those 3. So I guess in reality, it doesn't matter which one. I just pick one and use it. But I want to be lazy. I want to spot the one that's going to be most useful, the one that's going to save me the most time, so I won't have to go and do other things. So let's take a look at where we're going. We are heading towards tangent. Now, I have a fraction, right? Clearly, I'm playing with a fraction. And I eventually want this fraction to turn into tangent. So think about the top of this fraction. What's the top? What's the most beneficial thing for the top to be if I want to turn it into tangent?
Sine.
Yeah, definitely. I want a sine on top. Because if I can make this turn into sine over cosine, then I'm good to go, right? So my preference here would be to have just a sine on top and no cosines. All right, well, that tells me exactly which of these three I'm going to pick. I'm going to pick the one that has sines and no cosines. So I'm going to go ahead and put down in here 1 minus 2 sine squared. So I had options. I totally had options. But I chose this one because of where I'm going. So pay attention to that thought process, because I do that a lot. And not only do I do that a lot, I tell you about it a lot. I make use of where I'm going. I'm always thinking about where I'm heading and what kind of structure is going to help me get where I want to be. Right? And in this case, since it's tangent and I'm dealing with fractions, the whole time I'm going, I want sine over cosine. So I'm going to do whatever I can to get there. All right, well, let's see what happens now. So I'm going to erase these guys. Oh, that was a mistake. I didn't mean to erase those. Oh well. This means I'll write them up again. Good job seeing the next step. I guess in identities I see it, but sometimes on the whiteboard I don't. All right, so 1 minus 1 is going to go away. And then when I pass that minus sign through, I'm going to get 2 sine squared theta. And on the bottom, I still have 2 sine of theta cosine of theta. But now I can do some algebra. The 2's are going to cancel. The sine on the bottom is going to cancel with one of the sines on top. And I'm left with sine theta over cosine theta, which is our tangent. So we just proved that this identity is true. If you take the cosecant of 2 theta and subtract the cotangent of 2 theta, you actually just get plain old tangent of theta. All right, so just a little bit of an example of where we can use these double angle identities. And I chose this one on purpose to show you that when you get the cosine of 2 theta, you are going to have to make a choice. And sometimes there's a better choice than others. It still would have worked out. If we'd used either of the other two, we still would have gotten there. There just would have been more steps that we had to take. All right, so, you know, take Bruce's advice. Be lazy. Whenever possible, be lazy. When you're doing that. When you're doing. All right, so there you go. Little review of the double angles. All right, so here are the next set of identities we're going to create. And these are called the power reduction identities. And they are going to do exactly what they sound like. They are going to take sine squared, cosine squared, tangent squared, and turn them into things that don't have squares. We're going to literally reduce the powers from powers being 2, powers being 1. All right, so that's what these things are going to look like. Now, the way we're going to get them, this is actually kind of nice. We're just going to use the double angle identity for cosine. So now that I've erased them, let me write them back up again. So remember, we had cosine of 2 theta equals, I'm going to go to the two forms that have only sine or only cosine. There was 2 cosine squared theta minus 1. And the other one was 1 minus 2 sine squared theta. All right, well, to get these power reduction identities, we're just going to do a little bit of algebra on these two. So for example, start with the one that involves only sine. So I'm going to add 2 sine squared to both sides. And I'm going to subtract cosine of 2 theta from both sides. So that's going to give me 2 sine squared theta equals 1 minus cosine of 2 theta. And then one more quick algebraic step. We'll just divide both sides by 2. And we get sine squared theta is equal to 1 minus cosine of 2 theta, all divided by 2. And that actually is the power reduction identity for sine. So it's 1 minus cosine of 2 theta, all divided by 2. So notice what it did is it took a squared function and made it so that that function is no longer being squared. It reduced the power. All right, well, if you do exactly the same thing for the first equation, and you solve it for cosine squared, you end up getting something that looks almost the same. Except instead of having a subtraction up top, you have an addition. So kind of interesting that for both of those, sine squared and cosine squared, when you reduce the powers, it all comes back to a cosine. It's just the cosine of double the angle. Okay, so remember how I said before, we're not like really doing anything new. We're using identities we already have. This is what I mean. Like all we did was some algebra on these identities that we'd already built. So it's almost like they're not new identities. They feel like they're new, but they're not. They're equivalent to what I've got here in purple. It's just sometimes we want to reduce powers and we want to not have to do the algebra again. All right, so there's sine and cosine. So what do you think we do to get tangent squared? You've seen this trick a million times. If you know sine and you know cosine, you're going to get tangent just by dividing them. So we're going to take the sine squared over the cosine squared. So 1 minus cosine of 2 theta over 2 divided by 1 plus cosine of 2 theta over 2. So if you flip that over and multiply, you end up with 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta. All right, so there is your set of power reduction identities. There are a similar set for the other three. They're just the reciprocals of these. So just like all the rest of them, we only care about the big three. All right, now I'm going to tell you exactly where you're going to use this in calculus. Okay, so you can even write a note on here. This is going to be probably around the end of January, the beginning of February of 2022. Okay, so like 8 or 9 months away. All right, you're going to be working with this thing called an integral. An integral, it's one of the two things that you do in calculus. You take derivatives and you take integrals. Okay, so it's an operation. You're going to be doing integrals and you're going to be dealing with integrals of trig functions. And one of the ones that's going to pop up, they're going to say, hey, what if you have, say, an integral of sine squared or cosine to the fourth, or insert favorite trig function to an even power. And that quarter, let's see, I think that's going to be Larry. If you've not met Larry, Larry Green is the other calc instructor. It'll be Larry. And he'll say, hey, remember back in trig, the power reduction identities. And you're all going to look at him and go, nope, I do not remember. And then he's going to go, wait a minute, didn't you have trig with Bruce? And you'll say yes. And he'll say, well, didn't he cover them? At that point, you damn well better say yes. We just have forgotten. But they're going to come back there with a vengeance. All right. And the kind of thing you're going to need to do is what I'm going to show you with this guy. Let's say we start with cosine to the fourth. No, we'll do sine to the fourth. All right, so let's just say we've got sine to the fourth of x. But what I want are no powers. I don't want any powers whatsoever. So we're going to make use of the power reduction identity, and we're going to keep going until we don't have any powers at all. All right, now sine to the fourth, of course, is not sine squared, but we can write it as a square. If we think of it as sine squared, remember your rules of exponents. When you raise to another power, you can multiply them together. And now I can use my identity. What's in these parentheses is the same as 1 minus cosine of 2x over 2. And I'm squaring that. All right, so let's go ahead and square it out. So you need to, on the bottom, we're going to get a 4, of course, but on the top, you have to FOIL. And the result of that FOIL is 1 minus 2 cosine of 2x plus cosine squared of 2x. All right, so check out where we are versus where we started. It's definitely uglier looking, no doubt about it. It's got more terms, it's a fraction now. But I want you to look at the powers. We started with a power of 4. Now the biggest power you see is 2. We have reduced our power. Okay, but we're going to keep going because we've got another squared term. We got the squared term that's at the very end. So what I'm going to do is I'm going to use my my power reduction identity on that piece. So the first two parts are still the same, 1 minus 2 cosine of 2x. But now let's use this identity. So we're going to get, put this in brackets, 1 plus cosine of 4x over 2. And it's usually about this point somebody goes, wait a minute, 4x? Why the hell is there a 4x? But you guys are the strong silent types, so you won't ask me that question. But I know some of you are thinking. Anybody see why it's a 4x? Where the hell did that 4 even come from?
I'm assuming it's kind of working off of that 2x before it.
All right, so it actually doesn't have anything to do with this 2x right here.
Is it because of the 2 theta?
Yeah, it has everything to do with this identity. Look at what's going on. The angle that we're putting in our squared is getting doubled. So in this case, the angle that's inside our square is 2x. And that 2x has to get doubled. So when you have these identities, the other thing that is another recommendation, I guess, in general with identities, is also get good with the identities where you substitute something else in there, right? So like in this case, I'm putting a 2x in for my theta. So everywhere there's a theta, I think 2x. So I'm going to have to do 2 times 2x, which is my 4x. Now, let me just kind of simplify this a bit, get some like terms, combine it into one fraction, and all that. This is going to end up being 3 minus 4 cosine of 2x plus cosine of 4x. And that's going to be all divided by 8. So we started with a nice simple sine to the 4th. It is now turned into this monstrosity. But notice the powers. We have more than one trig function now, but the powers are both 1. And then in January, beginning of February, when you're learning about integrating trig functions, you're going to see that integrating this fraction, even though it's a big ugly fraction, the integral is crazy easy. Super easy. This first one, the integral, impossible. So this is a place where, and I hate doing this because nobody ever pays attention to it. And this is like the total dad thing, right? Where it's like, no, you'll understand later. When you grow up, you'll understand. I hate doing that, but it's truth. That is when you're going to care about power reduction. You're not going to care about it here in trig. Like we barely use it for other stuff other than simplifying. But when you get to calculus, and all of you are going there, I know this. These guys are your friend. So when it comes time, end of January, beginning of February, you're going to remember me saying this. So you're going to go, oh yeah, Bruce did say something about this would be useful now. And you're going to have to relearn it, but just be aware. All right, well, there you go. There is another set that we can add to our list. So now we have the power reduction. But like I said, they're not new. They were just that double angle kind of rewritten and reworked. All right, so the next set are what we call the half angle identities. Get ready, because these are going to surprise the hell out of you. They're going to start sine of alpha over 2 equals cosine of alpha over 2 equals And tangent of alpha over 2 equals what? We got half of angles in there. Yeah, so these are the half angle identities. So think of these like the double angle identities, except instead of doubling, we're cutting in half. So we're going to have some rules for these. But again, what they are, well, you'll see. All right, so to get these, we're actually going to use the power reduction. So here's what I want to do. Take that first power reduction, and instead of theta, let's put alpha over 2. So we're going to have sine squared of alpha over 2. That's going to equal 1 minus the cosine of 2 times alpha over 2 divided by 2. So it's kind of that same argument that I was talking about before with the doubling the 2x to get a 4x. Well, now we're doubling the alpha over 2. So we get 2 times alpha over 2. Okay, cool. So I can simplify that a little bit. Because 2 times alpha over 2 is just alpha. All right, so that's what that identity would look like if we had this half angle in. Now think about where we're going. I want sine of alpha over 2. Right now I have sine squared of alpha over 2. So what can I do to get rid of that square? And I'll give you a hint. It's not trig. What do you do to get rid of squares?
Take the square root of it.
Yeah, just take a square root. So we're going to get that the sine of alpha over 2 is equal to the square root of 1 minus cosine of alpha over 2. Yeah, we just take a square root, because that's what you do to get rid of squares. Okay, but there's something we have to remember to do when we take a square root. What do we always need in there, even though we usually forget we need it when we take a square root?
The plus or minus.
Yeah, we need to put plus or minus the square root of 1 minus cosine alpha over 2. All right, so when we develop this identity, it turns out that when you take that square root, we don't know if it's positive or negative. We'll talk about how you know whether it's positive or negative. But as it is right now, okay, well, yeah, it's plus or minus. All right, well, if you want to develop the other ones, you do exactly the same thing. Like for the cosine of alpha over 2, we put alpha over 2 in for theta, and then we take a square root. So you're going to get plus or minus the square root of 1 plus cosine of alpha over 2. And then for the tangent, you're going to get plus or minus the square root of 1 plus cosine, or sorry, 1 minus cosine of alpha over 1 plus cosine of alpha. So I'll go ahead and just put a little box around those. Because those are your half angle identities. All right. So if you ever want to cut an angle in half and know something about it, well, use the correct one of these identities and you will get them. So let me show you an example, and then we'll talk about the how do you know plus or minus business, because that definitely matters. But let's just say we're going to find the tangent of pi over 8. So pi over 8 is not on your chart. However, it is half of one of the angles that's on your chart. This is actually the same as the tangent of pi over 4 divided by 2. All right, so pi over 4, that's our alpha. That's the thing that we're cutting in half to get pi over 8. All right, so let's go to this identity. So tangent, we're going to get plus or minus the square root of 1 minus cosine of pi over 4 divided by 1 plus the cosine of pi over 4. And the cosine of pi over 4, we know. We know that number. It's on our chart. We can get it. But real quick, let's talk about, is it plus or minus? Because I don't want to have both possibilities. It has to be one or the other. And in this case, it's going to be plus. I'm going to erase the minus. Okay, so how the hell did I know that? How are you going to know that when you're doing it? How do I know that that's actually the plus? Well, it comes down to quadrants. Look at the angle that we're putting into tangent, pi over 8. What quadrant is pi over 8 in? Will help if it's in degrees, 22.5 degrees. That guy's in quadrant 1. Okay, so the angle that I'm putting into tangent is in quadrant 1. Because it's in quadrant 1, I know all the trig functions are positive, including the tangent. So that's actually how you're going to know whether it's positive or negative, is by looking at what quadrant your angle is in. All right, so now let's put in our cosine of pi over 4s. So the cosine of pi over 4 is root 2 over 2. So we get square root of 1 minus root 2 over 2 divided by the square root of 1 plus root 2 over 2. And I am going to simplify that just a little bit. And we'll go ahead and leave it like this. This is a fun way to see that answer. That right there, folks, is the exact value of tangent of pi over 8. It's the square root of 2 minus root 2 over 2 plus root 2. I just like these because it has what's called a nested root. There's a root inside of a root. I just find those kind of interesting. All right, so that's how you use these guys. But again, you got to really pay attention to what quadrant is your original angle in, the angle that we're putting in here into the, in this case, the tangent. All right, now, before I show you another example, I want to give you, there are a couple of other forms for tangent of alpha over 2. And I'm not going to build these for you. They're actually really easy to build. I think the book walks you through them if you want to see it. But there are a couple other forms that are a little bit more useful. All right, so the first one is this, where we've got the sine of alpha over 1 plus cosine of alpha. And then a secondary version that's very similar to this one is 1 minus cosine alpha over sine alpha. And when you're dealing with tangent, I like these forms better. And I think you can probably see why. No square roots. I don't have to worry about square roots anymore. I also don't have to worry about the plus or minus. I can just dive right in. So like, remember this example where we did the tangent of pi over 8? Alternatively, I could have gone with, let me just use this bottom one since it's closer. So the tangent of pi over 8 is the same as 1 minus the cosine of pi over 4 divided by the sine of pi over 4. And I can get those values. Again, I know both of those are root 2 over 2. And you can just trust me on that or check it yourself. But that ends up being the square root of 2 minus 1. Turns out that that is equivalent. These two guys are the same. I know they don't look it. You can eventually get there if you do a bunch of simplification on it. But you can see why these formulas can be a lot better than the first one, but we only have those alternates for tangent. All right, so there are our half angle identities. We're going to do another example with them, but let me put this on our list. Oh my God, that list is getting so long. So those are our half angle. All right, so let's play with another kind of problem that you're going to see on your homework, kind of thing that you'll see with these. Try not to erase the actual half angle identities. All right, but for this one, all right, so here's what we know. Given that theta is in quadrant 4, and that the sine of theta equals 7/9, I want to find the cosine of theta over 2. Okay. Real quick, the sign needs to be negative 7/9. Sorry about that. It should be a minus 7. All right. So here's what we're going to do. Let's start with the identity. Right? If I want cosine of theta over 2, I know that it's going to equal plus or minus, we'll worry about the plus or minus in a second, square root of 1 plus cosine of theta divided by 2. So let's just start here. I need to know the cosine of theta. But I'm not told the cosine of theta. I'm told the sine of theta. But hopefully you guys remember that we can always do this. If you're given a trig value, you can find all the rest. So for example, if I want to find cosine, I'm going to use the Pythagorean. I know that the sine is equal to minus 7/9. So when I square that, I get 49/81. Subtract that over. I think that's 32/81. So the cosine of theta is plus or minus 4√2/9. Okay, but I need to know if it's plus or minus. So let's think about where theta is. Theta is in quadrant 4. And in quadrant 4, cosine is positive. All right. So I now have a number to plug in there. So this is going to equal plus or minus the square root of 1 plus 4√2/9 over 2. Okay. So this, of course, can get simplified. We'll just go this far, 9 plus 4√2/18 inside of our root. But I still need to worry about, is it plus or minus? All right, so now let's think about where theta over 2 is. What quadrant is that in? Now be careful. Don't say quadrant 4. Even though originally I said, hey, we've got a quadrant 4 angle, because remember the quadrant 4 angle was theta, not theta over 2. So do you think we could figure it out? How about this? Okay, so here's quadrant 4. What angles form the boundaries for quadrant 4?
$270 to $360.
Okay, so in degrees, it'd be 270 degrees to 360 degrees. In radians, it'd be 3 pi over 2 to 2 pi. I'm going to stick with radians, but Daniel, there's nothing wrong with going to degrees there. So here's what I know about theta. I may not know exactly what it is, but I do know that it has to be between those two angles, or at least is coterminal to one. That's between those two angles. All right. Well, remember what I want is theta over 2. So let's cut those in half. 2 pi, if I cut that in half, is pi. 3 halves, if I cut that in half, let me write it down here, is 3 pi over 4. So theta being in quadrant 4 gives me this, which tells me theta over 2 is between 3 pi over 4 and pi. So let's think about where those are. pi, of course, is right here. Where's 3 pi over 4? So pi over 2, 3 pi over 4. All right, so what this tells me is that theta over 2 is somewhere in there. All right, so that's second quadrant. I know that theta over 2 is actually quadrant 2 angle. All right, well, that gives us the answer to plus or minus. In quadrant 2 is cosine plus or minus.
Negative.
It is negative. So there you go. So even though we don't know the angle at all, we didn't know theta, we don't know theta over 2, but because we knew where theta was and a trig value for theta, we actually know the cosine of theta over 2. This is a very challenging question. These are probably the most difficult kind of questions you're going to have to do, finding exact values, because of the having to decide the plus or minus. And that's going to be dependent upon where the half angle is located, not the original angle. And it's really easy to get those confused. All right, so today we added 2 more sets of identities, power reduction and half angle, but power reduction came directly from the double angle and half angle came directly from power reduction. So it wasn't like anything new had been developed, really. All right, but now we can cut angles in half and we can double them and we can do like add and subtract. We can do a lot with them to develop more things. All right, so next time we're going to finish this out. We're going to put 2 more groups on here, product to sum and sum to product, and then be done developing identities. But next time we're also going to have our quiz, right? Because I decided to switch quiz and exam weeks. Just reminding you all again, I sent out a Canvas message earlier today reminding you of that as well. The quiz on Wednesday is going to cover sections 8.3, 9.1, and 9.2. So what that is, 8.3 is the inverse trig functions. And then 9.1 and 9.2 are identities. 9.1 was just we're playing around with the old identities to simplify and all that. And then 9.2 is the introduction to the sum and difference of angles. Okay, so I'm not going to ask you to do anything that requires double angles or power reduction or half angle or anything like that. Okay, so it's just going to be sum and difference of angles, general identity stuff, and then the inverse trig. Okay, so we're gonna have our quiz on Wednesday, which means starting at 11 o'clock, that will open up. We'll have class starting in here at 11:40. All right, and then at that point, after we go over any kind of homework questions, then we'll dive in, we'll knock out the last of the identities. So that we'll have that entire set ready to use whenever we need. All right, so with that, I hope you guys have an awesome couple of days, and I will see you all on Wednesday.
Thank you.
Thank you.